Okay, so we saw an example using Zeno's paradox of something called a geometric series. So let's formally define what the heck that thing is. So a geometric series is of this form. You got the summation from n equals 0 to infinity of a times r to the n. So let's talk about the different parts of this. Like if I were to stick in 0, the r is 1, so it'd be r to the 0 power, which is 1 times a. A is our first term. So that's the first part. A, that number that's right there, is in fact the first term. Now, it's only the first term when n starts at 0. If n started at 1 or some other number, in order to get what the first term is, I would just have to plug that number into the formula here. Let's say it's 1. I plug in 1 into that formula. It'd be a times r raised to the first term, and that means that our first term is actually a times r. It's this one that's over here, okay? Sometimes I need to know that, and as you'll see in a little bit, it's part of the sum of this particular series. Okay, the other key part to this is the r. The r is the common ratio of the consecutive terms. What that means is if I were to divide two terms in order, ar divided by a, the a's would cancel and you'd just be left with r. If I take ar squared and divided by ar, the a's cancel, a factor of r will cancel, and I get r again. So if I divide any two consecutive terms, I get this common ratio of r. So remember that there are two key questions, two key concerns whenever we're talking about series. The first one is, does the series converge? In other words, does that sum get closer and closer to some finite number, or does it shoot off to infinity? Does it diverge? The other one is, if it does converge, what does it converge to? And that second question is often a little bit harder to figure out, unless it's geometric, because geometric series, I'm going to show it to you right here, okay? How to sum up an infinite sum of numbers when they are geometric in nature. Geometric just means they have a common ratio. You're multiplying each term by something in order to get the next term. In the previous one, our common ratio was a half. We were multiplying by half each time. I took 1, took half of it, got a half. Took half of that, got a fourth, and so on. It was a geometric series. Okay, so we want to find the sum of the geometric series, and it's just written in general like this. So how do I start with a sum? I do our nth partial sum, so like we did before, but we're going to work this out a little bit differently. This is an algebraic technique that someone came up with that allows us to figure out very, very easily with a formula what the sum of this series is supposed to be. So here's the nth partial sum. It looks just like it was defined before, where it's a plus a times r plus a times r squared and so on, all the way to the nth term. And so you might be going, well, why is the power on n, on the nth one, n minus 1? And the reason why is because we started at 0. We started at 0, we didn't start at 1. If we had started at 1, then that last one would be to the nth power. Okay, so here's the trick. I'm going to take that equation that we just wrote down for the nth partial sum, and I'm going to multiply it by r. Why are we multiplying it by r? Just go with it. You'll see what happens here. Now, I have two equations, and I'm going to take these two equations. Look, there's lots of terms that exactly match up. I'm going to take these two equations and I'm going to subtract them. So I'm going to subtract the top one minus the bottom one. And over here on the left-hand side, of course, I'm going to get s sub n, the nth partial sum, minus r times s of n. But on the right-hand side, lots of stuff is going to cancel, like the a times r cancels, a times r squared cancels, and on and on and on. Everything's going to cancel except for the first term, a, and then the last one, which is a times r to the nth power. And remember that on the second one, that second line, it's r to the nth power because we multiplied it by r. When I multiply this term by r, it would be r to the n minus 1 times r to the first power. You add those exponents and you're just going to get to the nth power. Okay, we're going to subtract those, and here's what the sum turns out to be. It's actually really nice. This is why somebody figured out, or how somebody figured out in order to come up with a sum. If you look on the left-hand side, we have the nth partial sum that we can factor out. That's exactly what we want to do because we're trying to find a formula for the nth partial sum. I factor it out, and I'm going to divide by 1 minus r so I can get it over to the other side, and I'll have myself a formula for the nth partial sum for any geometric series. Okay, now what do I do with that? I now want to take the limit as n approaches infinity of that nth partial sum, because whatever that limit is, that should be the sum of the series. That's assuming that it actually converges, right? So I want to take the limit. I'm going to kind of rearrange some things here. The first thing to notice is that the a times our a divided by 1 minus r, it doesn't involve an n. That means the limit doesn't affect this. I'm going to take that term and I'm going to bring it outside of that limit. And I'm just going to be left with the quantity 1 minus r to the n that I got to take the limit of. Okay, so I want you to think about this r that's over here. We're taking this exponent and we're making it bigger and bigger and bigger. So it's like an exponential equation, right? So what has to be true about the base on that exponential equation if this thing is going to diverge versus converge? Well, from exponential growth and decay, if you put it in those kind of terms, I know that I have exponential growth if that number is bigger than 1. And so there's the place that we're going to start. So if your R value, specifically if its absolute value is greater than or equal to 1, it's going to diverge. So if you're wondering about the positive 1, why are we going to include positive 1 here? If r is the common ratio of the terms, this means that if your r value is getting closer and closer to 1, it's as if you're adding up what's closer and closer to the number 1. 1 plus 1 plus 1 plus 1 plus 1. What's that going to add up to? It's pretty much going to add up to infinity. Okay. All right, and it also works for the numbers, the negative ones as well, like negative 1. Here, that one's going to, depending on the power, is going to oscillate. And that's bad for limits too, right? That's one of the ways in which a limit does not exist if it oscillates. Okay, how about converging? Converging is if it's going to be an exponential decay. So exponential decay is going to happen whenever it's between, say, 0 and 1, when it's a fraction like that. But it also works for the negatives. So the way that we state this is that it converges if the absolute value of r is less than 1. And then the limit there is going to converge to 1, right? Because that term there, the r term, is going to go to 0. Exponential decay, it's going to decay down to 0, and I'm left with just 1 for the limit. I'm left for 1 for the limit, which means that it's 1 times this fraction that's right up front, which is a over 1 minus r. And guess what that is? That's correct. That is the sum of that infinite series. Okay, so here's something to take note of. Convergence of geometric series. A geometric series with common ratio r diverges if the absolute value of r is greater than or equal to 1. But if the absolute value of r is less than 1, then the series is going to converge to, specifically, a over 1 minus r. A is your first term, and r is your common ratio. And there is a note there, it's always, absolutely, on the AP exam in some sort of capacity. Over here on the right-hand side, I'm going to take a moment here and explain this geometric interpretation of the same exact sum that we have here. And I also want to take a moment to explain those absolute value inequalities. A little bit of algebra explanation for each one of those. Okay, so let's start with those algebra explanations of the inequalities, absolute value inequalities. So the first one is the absolute value of r. Actually, let me do this on a blank slide here. So the absolute value of r is supposed to be greater than or equal to 0. Remember that this means it diverges. And I want to get a handle on every single value of r, like so that when I see it, I know exactly what that does. Does it diverge or converge without actually having to fit it into this little inequality here? So it's an OR inequality. An OR inequality splits up as two rays that go in opposite directions. It is r is greater than or equal to 1, or it's r is less than or equal to negative 1. On a number line, you got your 0 in the middle, you got your plus and your minus 1, and you've got open circles around, no, these are closed-in circles. Yes, we color them in because it's equal to, and then it's the stuff that's on the outside there, right? So any of those numbers that thing is going to diverge. If, on the other hand, it's the absolute value of r is less than 1, notice there's no equal sign there, it's the part that's going to be in the middle. This is an and inequality, less than, and that's going to be sandwiched in between a -1 and a +1. And on the number line, if I use the same kind of number line that I did before, it's the stuff that's in the middle. Now this one will get open circles around the -1 and the +1, and that's the stuff that's in between there. Even the negative ones, all of that stuff is going to converge for geometric series. Okay, and then specifically it converges to this, this little simple formula, first term over 1 minus r. Now, another thing I want to point out is that a is the first term, as I mentioned before, only when n is equal to 0. If, and they sometimes do this, start your series at n equals 1 in order to get that first term. It's not just going to be this a that's right there. You need to put the 1, if that's the case, into your formula so you can get the first term that's supposed to go on top. Okay, so now let me take a minute to explain this geometric picture that's over here. So you construct the picture so that the triangles are congruent. Are not congruent, sorry. The triangles are similar, and specifically the similar triangles that I'm talking about are the large one here and the one that's left over on the left-hand side here, the smaller one. These two triangles are similar. And remember what it means for similar triangles, it means that the ratio of their sides are proportional. They have the same ratio. Specifically, it's like the ratio of r, right? We're talking about a common ratio of r. So I can, notice that the s that's over here, it's a plus a times r plus a times r squared plus a times r cubed. It's the sum of our series. So if I take a ratio like small to big, so that's s corresponds to the larger side on this side, which is a, is equal to the small to the small, which is a over, that's this a, over a minus ar. All right, and now I want to solve this formula for s, so I'm going to multiply the a over, and s is equal to a squared over, and I'm going to factor the bottom. I'm going to factor the bottom because it has a common factor of a as a times 1 minus r. And then notice, of course, that a factor of a cancels out, and we get the formula that we have right here. Okay, so in the next couple of videos, what we're going to do is we're going to take a couple of examples of a couple of geometric series, see if they converge, see if they diverge. If they do converge, what's the sum of that series?